Now today we're going to do section 3.5, but before I start, I want to show you something I bought in a grocery store that has nothing to do with this class. Check this! Millennium Falcon gingerbread kit. Yay! Look at how awesome that looks. I got it at the grocery store. Okay, I also want to show you the back side. See? Yeah. All right. So anyway, that's what I found. Okay, it's like digging out, looking and finding treasure. Look at how cool this thing is, right? And the other side too. But anyway, that's all I want to show you. So let's get back to the hard work. Please turn to page. Give me a second. Okay, I found my page 261. Please turn to 261 and we'll start at example 5 because the other examples are too tedious. So then, whereas the concept is quite simple. Let's consider, for example, f of x equal to x squared. Now, while we're doing this section, we want to move the graph around, okay? Like moving it this way or that way. So let's consider how that might be moved. There are two ways to move this thing for now. First, we'll move it left or right, and then we'll move it up or down. So for left and right, let's consider, for example, f of x equal to x squared. Now that is just some function that we've seen several times already, right? It looks like that. It's a bowl. And then what we're going to consider is, what if we want to do f of x of, where is x minus 2? Oops. 2, please. Okay, so we're doing f of x equal to x minus 2 squared. That is x minus 2. Okay, that is, we want the input to change from x to x minus 2. So then we will do that. See, put x minus 2 where x used to be, we get this function. But what would the graph look like? We can, what happens is then, it used to be that this function where x is 0, y is 0. Now, in the new function, for the value to be, to reach the same result, x has to be 2 now. See, if x is 2, then 2 minus 2 is 0, y is 0. In other words, this graph, at the tip, we always look for some special point to move it with. Okay, at the tip here, the tip now is over here. Okay, is same graph, look exactly the same, except it got moved over to 2. Where it used to be as 0. And that's how we normally move stuff left and right, is we subtract it by a number, okay? Now in general, here it is. F of x minus a, if a is positive, like in this case, 2 is positive, okay? We're subtracting by a, remember that. So 2 is a, okay? So if a is positive, as in this case, our graph got moved to the right. If a is negative, then the graph get moved the opposite way. And that's how you move graphs left and right. Now the next sample I want to talk about is what if we want to move it up and down? Like, for example, what if we have a next different function? Okay, let's call it g of x. G of x is just equal to, say, x squared, and let's call it plus 3. All right, we want to make it, so g of x is the same as f of x, except you got 3 more. So what would the graph look like? So let's plot it again. Okay, now, my marker seems to be passing out. Anyway, so g of x, when x is 0, okay, it used to be here, and then now it is 3. Okay, so then, that's the new graph. But otherwise, is g of x, basically everything in here, you will lift up 3 units. So g of x looks like this. See, where it used to be at the bottom, and the bottom is up here, and now is 3 units high. So that's the principle behind it, is that if you have f of x, you plus b, let's ignore this for a second. If you add the function to it, what you did is, if b is plus, then you lifted it up, and if b is minus, you pushed it down by the amount of b. Okay, so that is how you move stuff left, right, or up and down. And if you plot a few graphs, then you will see exactly why that is the case. Now you might wonder, why do we even care? Why don't we just type this in the Desmos graphic calculator and it'll pop right out whether it's going up, down, or twisted, or whatever it wants to do. This is these things are a trick to plotting graphs from back when the graphics calculator was not invented. So this is handy to know. However, as you notice, there's the plus minus left to right. It's very difficult to remember for most people. And so so what I want you to do in this section is just go through the homework and do as you're told. Look at the chart. Here's a chart that tells you left, right, and all that. And after that, don't worry about it. If you can't within a second remember, oh, is it the plus is left or right, or was it up, down, or something? And that is, I just want you to have an impression of this stuff, so you have an idea, and that's all you need, okay? That things move this way or that way if you do stuff like this or that to it, or up and down, okay? So for this section, simply just go through the examples and do the homework, and then when you're done, don't worry about it anymore. Okay, it's not necessary to know it inside out. Unlike the chapter 1. Chapter 1, I totally want you to know it inside out. And at any time you don't remember it, go back and review it again. Okay, that's true for chapter 1 and the first part of chapter 2.1, I believe, because that's talking about equations. So the entire chapter 1 and chapter 2.1, first half of chapter 2.1 about equations, I want you to know it inside out. This stuff, we'll look at it and then we'll get over it. All right, so let's move on. Example 7. This is on the following page. Did we do example 6? What did we do? Let me see. 5. Oh, skip. Okay, we did example 5. So we're going to skip example 6 and go on to example 7. Okay, and on what page am I on? I am on. So now on the following page, so 262. So let's look at example 7 and following these principles here. Now the example 7 says that we have f of x equal to absolute value of x, and we're supposed to base on that and sketch the graph of some other function that is made by shifting the original function left, right, up, down, something like that. Okay, so let's do that. First, we know that f of x looks like. This comes from a previous page where there's toolkit functions. This is one of them. Or you can just Google it. F of x equal to absolute value of x looks like this, okay? A giant V shape. That's all it looks like. I'll stand over here. So that is the absolute value of x. And what we're trying to strive for is first, we need to do f of x plus 1. That means plus 1 just means you're subtracting by a negative, okay? So it's moving to a is now, in other words, for a now equals to -1. So then x minus a, it becomes x plus 1. So if a is -1, we'll shift this thing to the left. So here's the first shift by 1, okay? Here's -1. It used to be 0, or move it to the left by a, which is well, anyway, that we'll shift it to the left by 1 unit. And then the next value is b. It says b equals to -3. Now remember for b, or check this, for b, plus means shift the graph up, negative, shift the graph down by the amount. So the next step of the graph shifting is it used to be here, we'll move it down 3 units. But otherwise, the graph still look the same, something like that. So this is at the location -1 and -3. Okay, that's where the tip is. And that should be the final graph of whatever it is that we want. Let's look at the final graph. And as you can see, yep, your book plotted something, see, compared to what I have, similar, right? So that means I got it right. All right, so that is for that example. And next, let's look at example 8 on the following page. We are on now page 263. Okay, and let's do example 8. All right, so combined vertical horizontal shifts. Well, I thought that's what we did before. Okay, let's look at it on the following page where we have this thing, and we're supposed to draw. What are we supposed to draw? Does it even say? Let's see, what does it want? Oh, I see. We're supposed to look at the graph and write the equation for it. So we're doing the opposite. Instead of looking at the equation and then figure out where the graph goes, now we're given the graph. Okay, here's the graph. And we even know what it is, the square root of x or something like that, right? Yeah, it's the square root of x. We're supposed to write the equation to show that shift. So let's look at this thing. First, it shifted to the right by 1 unit. So the thing is, so it's the square root of x, okay? And then it shifted to the right by 1 unit, so we're going to subtract by 1. Because we're subtracting, if it's to the right, we're subtracting by that amount, okay? And so, and then we're shifted up, as you can see the graph, by 2 units, so plus 2, and that should be the answer. Let's look at it. Yep, it is, and that's example 8. Next, we are going to talk about something called reflecting across the axis. That is, to see what that means, let's look at an example, okay? And then now we're looking at the square root, example 9, where we're looking at the square root function again. So we have the square root function. What happens when we reflect this thing? Then, let's see, what is that? Okay, first we're going to do the negative reflection. What I mean is that, let's say f of x equal to the square root function, okay, which is the square root of, what do they want? They want t, which is fine. Let's rewrite it as t. It doesn't matter what you call it, okay? A function, the input, the variable names can be changed. It's like naming your kid Mary instead of Jane or something. It's all the same. S of t, so our function says s of t equals the square root of t. Okay, so that graph, if you look at the chart or plot it in some calculator, the chart looks like this. Well, it doesn't go down actually. Yeah, it keeps going up. And anyway, so here's our square root function. And what do we want? We want to reflect this thing down. To reflect it down, then every positive value before now is a negative value. So the way we do it is just slap a negative sign in front of it. Because then, for example, it used to be that when this is 1, okay, this value is 1, right? Positive, because the square root of 1 is 1. So if we slap a negative value in there, so you take, it's still square root of 1 is still 1, but now the function wants you to put a negative sign on there, which means now your function looks like this, the mirror image of that thing, but it got reflected to the bottom. So that's the reflection across the x-axis. All right. And then another reflection is, what if we want to reflect it across the y-axis? You might say, I'll never want to do that. Why would I want to do that? But let's say you did, okay? And so or we just want to see what it looks like to reflect it across over here. So then this thing looks, it used to look like this. To reflect it this way, now it looks like this, okay? The same thing, except they pretend this is a mirror, okay? And the mirror image looks like this. Now, how would you come up with that? That then the s of t would become, I shouldn't call this s of t. This is a new function. This is the reflection, okay? So we'll call it, I don't know what we'll call it, but that's the reflection across the x-axis. Maybe we should call it, I don't know, I'll call it sx of t. That means we're reflecting. This isn't the s. This is the s reflected across the x-axis. And I just made that up. It sounds pretty good, doesn't it? Anyway, so now let's reflect across the y-axis. So we'll call it as y of t, and that would be, how would we reflect that? Then what we're going to do is put a negative sign on the inside, because the square root function normally doesn't work for negative numbers. But if you stick a negative sign in here, then every negative number becomes positive. So then that's why it's the reflection on the other side. So that's how you, in general, reflect things across the x or y axis. So next, let's consider on page 266, problem, example 11. And look at this stuff. Now we have a function that's given in a table form, okay? Here's a function and it's only defined for 4 values. And the question is, what is, okay, fine. What are we doing? We're trying to figure out a function where it is equal to negative f of x. What would that be? we need to write down the results on the table. Well, that's simple enough. Okay, it already told you it's minus f of x. This is a negative sign. And so let's slap the negative sign on there. So 2 becomes minus 1, 4 becomes minus 3, and 6 becomes minus 7, and 8 becomes minus 11. That's all there is to say about it. Now the next question is that's the g of x equal to negative f of x, part A. Now part B is more tricky. Now we need to figure out h of x equal to f of minus x. So now we're looking for this thing, okay? What is f of minus x? And find a chart for it. Well, f of x, notice that it's only defined for 2, 4, 6, 8. So we can't say, well, what's f of minus 2? We can't do that because we don't even know what it is. But here's what we do know, okay? We do know what f of minus negative 2 is, okay? So what happens is now we're going to draw a new chart where we have negative 2, negative 4, negative 6, and negative 8. Why? Because if we put negative 2 in this value, it becomes positive, and we do know what f of positive 2 is. Okay, so this is the new set of numbers we come out with that will make f work. So f will work from f of negative x will work on negative 2 because that's f of positive 2, which is 1, as we know. So the answer to this is 1. And similarly, this one, okay, you stick the negative sign in front and knock out the negative sign. And so this value is 3, and so on, and 7, and 11. So f of negative x can be defined like this, and it's only defined for these 4 values because f of x itself is only defined for the positive values, and f of negative of x can only then be defined for those 4 negative values. And that is the answer of example what, 10? Yes, right? Oh, did I? Yeah, that's right. See, that is what the book says as well. So next, let's look at example 11. Let's see, example 11 on the following page. No, same page. I'm still on 267, page 267, all right? And then let's look at this thing. It has a specific formula. I'll copy it down here, where k of t equals to something. Negative 2 to the power minus t, and then plus 1. Now, if k of t is that thing, what are we doing here? We are supposed to plot this thing, okay? We're given the function just 2 to the power t. Now, here's the function 2 to the power t. Notice the blue line comes down, seems to touch the x-axis. It doesn't. It only gets very, very close to it. But because the blue line is so thick, you can't see that it's not touching. But it doesn't touch. In fact, it never touches. Okay? So not that matters. That's just a point of interest to tell you. That's the quality of 2 to the power t. But this is just 2 to the power t. So I'll draw that 2 to the power t here. So here's 2 to the power t. We'll draw like this. And I'm not going to let it touch. In reality, it's a lot closer than this, okay? But I will keep it not touching, so to remind you that this thing doesn't touch. Not that we care about that right now, whether it touch or not. The point is, however, is that we know this, and we're supposed to come up with that. So we're going to use our bag of tricks that we have learned to try to get this thing out of this. Okay, so what we're going to do is each step. So first, 2 to the power t looks like that. We need a negative t. So what is 2 to the power minus t look like? Just this function, okay? 2 to the power minus t, it says that if you stick f of minus x in there, that is, you replace x with minus x, you will end up reflecting against the y-axis. Which is the y-axis? This one, right? This is the y-axis, so we'll reflect it this way. Okay, so please pretend this is the mirror, and we'll do this. Okay, this thing slant down exactly like that one, except that it's on the other side now. So this is 2 to the power minus t, and so far so good. Next, we're going to slap a negative sign in front. Now, slapping a negative sign in front is the same as reflecting against the x-axis. as we have mentioned a little bit earlier. So we're going to reflect against the x-axis. This is the x-axis, okay? So this is now the mirror. I'm going to imagine the mirror image of this thing. You know, here's the lake, here's your mountain. What does the reflection look like? So then we're going to do this. So then the reflection is going to go down like that, okay? This is negative 2 to the power t, negative t, okay? Because we're reflecting this one. Okay, so far so good. And then we still need the plus 1. What about plus 1? Plus 1 is when we're adding something to the function. When you add a number, if the number is positive, you move the graph up by that much. So we're doing plus 1, so we'll move it up. Okay, so here, let's move this thing up. It will be something like this. Okay, 2 to the, this is, now we have the final result. So we got from here, okay, we moved it up. So we have minus 2 to the power minus t, and then we moved it up 1 unit, and now that's the final result. And that is the k of t that we're looking for. Now all this stuff was done back in the day when there was no graphics calculator. Nowadays, of course, you can just type this thing in a few seconds and not have to worry about all the stuff, especially what if you reflected like by the wrong axis by mistake or something. And but it's still good to know how to do this. Okay, it's just a skill that is you don't have to know it, but it's good that you do. I mean, for example, on Star Trek, Captain Picard used to be a pilot, and of course, once he becomes the captain, he doesn't pilot the ship itself anymore. But there was one time where they were in a very tight situation where the average pilot won't do, and Captain Picard actually sat down and piloted the Enterprise. This is the same principle that we don't need to know this stuff so much anymore, but it's still good to know that, you know, on a matter of principle, that if you're studying algebra, you should at least be aware of this stuff. But on the other hand, like I said before, don't make a big deal out of it, okay? Yeah, this is good enough. Anyway, so let's go to the next page. The next page we're going to talk about is called even and odd functions. The even and odd functions, what it means is whether this thing is symmetrical or not. For example, if you have y equal to x squared, this is an even function in the sense that this thing is symmetrical across about the y-axis, right? In a way such that if you have y equal to a negative x, if you change the sign, that is still going to be the same because it got squared. So in other words, the function is equal to if you were to stuff a negative sign in there, and that is called the even function. Okay, and in a similar situation, but not completely the same, let's consider the function xy equal to x to the power 3. So that is y equal to x power 3. Now, in this case, we have, if you stick a y, and if you replace x with a negative x, then what you have is negative x to the power 3, okay? And being that it is multiplied by 3 times, your negative sign is still there when you're done with it. So then that equals a negative x to the power 3, which is the minus of the original function, okay? Minus f of x. I should have, see, y is f of x. In that case, then, now in this situation, where if you slap a negative sign into the x, it ends up being a negative of the original function. That's called an odd function. So this is called even, and that is called odd, okay? Well, that is the way it is. So let me erase the board. Next, let's look at example 12 on page 269. We have a function here, and the question is it even or odd or neither? It doesn't. A function doesn't have to be either one. Okay, most of the time they're not one of them. And then, but we're going to test it. We'll test it to see if to test for evenness, we'll stick the f negative x in place of x and see if it equals to the original function. If it does, it's even. If it doesn't, then it's not even. So let's do that. So if we're gonna stick the negative x in there, okay? And let's see what happens. So that becomes minus x cubed, right? Because you have 3 negative signs together. and then becomes negative signs again, and then there's one negative sign, so that changes to minus 2x. Now this does not look like the original function at all, therefore the answer is it's not even. So so no for that one. Next, let's check if we slap a negative sign in front, what would happen? So f of if we slap a negative sign in front, we will did I get that right? Let me check. Yeah, I thought that didn't look right. There should be a negative sign here. Okay, otherwise what are we doing? So then so anyway, let's check the second rule is if we change the sign, does it become the negative? Well, we already did that, right? And so what is this? This is exactly the negative of that thing, right? This is equal to minus f of x. As a result, then this is so it is odd. So the question as to odd would be a yes. Right, so this is an odd function, okay, but it is not even. So that's the answer. Next, let's consider something called stretches and compressions. Now for stretches and compressions, let's flip a couple of pages to page 271. What we're going to do is take a function and then multiply it by some number and see what happens to it. If the number is bigger than 1, it will make the function bigger, okay? If it's between 0 and 1, it will make the function smaller. That's the idea of stretching and shrinking. So that's talking about the vertical ones. So let's look at an example, okay? So now let's look at example 13. Example 13 is, okay, flip on to, now we're at page 272. And with this example, just have a function that's in a graph. Let's look at the graph on page 272. See, we have that function, and what are we going to do with it? We are going to, let's see, let me figure out what we want to do with it. It doesn't say. It said, oh, I got it. Finally, it says we want to multiply everything by 2. In other words, look at the function, okay? 1 will become 2, okay, at the first point. And then at about 3, the function at 3 becomes 3, right? Now it's going to be 6 because it says multiply by 2, double everything. So, and then the function at 6 equals to 2, now it's going to be 4. The function at 7, 0 is still 0, okay, because twice as 0 is still 0. And so when you're done, your new function looks like this. See, everything got doubled. But otherwise, nothing is interesting is going on. So the function got stretched. You visualize it stretching vertically because the function that you're increasing it by is the number you're doubling it. So a is 2, which means you're stretching it. What if a is 1/2? Okay, then you're going to crush everything into half of what it was before, which is example 14. Here's a table. All right, so f of x is a bunch of values, and what we want to do is take the output and reduce it by half. So we got this instead. We got a bunch of halves as a result of reducing everything by half, and that is your answer in reality. So that's the difference between that's the definition of vertical stretch. You expanded it or you pressed it down, either way, okay, by a certain amount as given that is required from you. Okay, so now let's look at example 15. Now next, let's consider example 15 on page 273 or 4. Now we have a function that we're given a graph thereof. Okay, here's a graph on the page, right? And it looks like y equal to x to the power 3. If you're familiar with the graphs that we did in the so-called the toolkit functions a few sections ago. But if you don't remember what it's called, it doesn't really matter. It does tell you that this comes from x to the power 3. However, how does it adjust? Like it got stretched or something, okay? So we need to adjust, find the a such that it fits the function that's in the graph. So let's look at this, okay? If you look at this thing carefully, you notice that when x is 2, positive 2, y is also equal to 2, right? And okay, that's interesting because normally for the function for y equal to x to the power 3, then if x is 2, y is going to be 8, right? And so, but in this function, it looks like it, but y is only 2 when x is 2. So what we're going to do is calculate what a is, okay? So the function is going to y equals to ax cubed. We just don't know what a is, but we're going to plug in 2 and 2 in there, in the sense that when we know this much, that when x is 2 for the function, y is also equal to 2. That is, that point is on the function. So let's put that in and see what happens. And so this is a times x is 2, okay? 2 to the third power is 8, and y is going to be equal to 2. Now that means a equals to 1/4. If you push the a across the equal sign down here below the division line. So a equal to 1/4. In that case, then of the function we're looking for, then let's call it g of x. The new function that comes from this thing is actually equal to 1/4 x cubed. That's why it's in other words, it got squashed. Okay, that's why when it's 2, it only made it to 2, whereas the other function would have made it to 8. So so this is a compressed function from what it was anyway. And so that's that. And next, these are vertical compressions that we've been talking about. So next we're going to talk about horizontal compressions, okay? How functions can move this direction. And it compresses in a similar way in that horizontal compressions is follows the formula like this. Let me write it down. Now, the horizontal compressions or stretches, they mean the same thing, okay? Compression is just a smaller stretch or negative or something. Anyway, you're pressing it this way or that way. And so the horizontal compression, the only difference is now the number that you're multiplying is going to be inside the function, whereas before, for vertical ones, is on the outside. So let's look at an example to see how this works. Look at example 16. And we're looking at some fruit flies, okay? So look at example 16. We'll look at, let's go to page 276, where we look at the graph. So we have page 276. Look at, this is example 16. Well, anyway. Now let's look at the graph. What happens here is, and all your input, I think, got reduced by half. So the height is the same, okay? But you're pressed together left and right. That is, what used to be 7 and is now 3.5. What used to be 3 is now 1.5, and so on. So your entire graph stays the same height, but it just got pressed into half, okay? It got a lot narrower. So that's why they look somewhat similar, but not quite. And so that is how you do a horizontal compression. So with that, let's look at example 17. Now, problem 17 on page 276, we have, I think, the same thing we looked at earlier, okay? There's f of x. It only has defined on 4 values in the domain. So that's all we know about it. And we're supposed to come up with g of x, and that would be the f of 1/2 of x. And how are we going to do that? Then g of x then will be, we'll choose the input to be half of, in such a way that still fits, okay? So being that it's 1/2 of x, we'll choose 2. We'll choose something that fit into the 2, being that f is defined at 2. So we'll choose 4, okay? Because if you plug in the domain, we'll choose 4, because 4 divided by 2 is 2, so that will give the value of 1. So 4 will give the value of 1. Similarly, if we choose x to be, basically we choose x to be double of what the domain was before. So at this one, we'll choose 8, because 8 divided by 2 is 4, and f of 4 is 3. So we can write down for g, this is our new function g, is going to be like this. Similarly, we have 12 here, okay, divided by 2 is 6, and f of 6 is 7. So we have g defined as 7 there. And then finally at 16, g will be defined at 11, and that's our new function. It will be defined at a different domain than f, because that's the only way we can get it to make sense. Okay, so that is our new function g for example 17. So next, all right, example 18, we are doing a horizontal compression of What is that? Okay, so we have a graph. We have, in fact, 2 of them. So let's look at it. Now, first we have, what is that? Okay, the blue line is f. F looks fine, right? And what's with the orange line? It got really squished in there. So the blue line started at 6 and it got squished all the way down to 2, which means it is multiplying by 1/3, right? So that is basically the answer. Okay, we'll divide everything by 1/3, or put it another way is that well, anyway, where does it say G is 1/3 F? Can't find it. Well, whatever. And put it another way, you can also say that the horizontal compression is by 3, which means, okay, to write it down, we have to write it this way, okay? Then G of x is equal to, G of x in this case, the 1/3 is written actually in here as 3 times. And does that, let's see. So when, does that make sense? Let me think about this. Actually, it does make sense. For example, let's consider G of 2, right? And so G of 2 is equal to f of 3 times 2 is f of 6, which is equal to whatever it's supposed to be. F of 6 is 4. As you can see from the graph, then G of 2, right? The orange line, G value at 2 is equal to 4, whereas F value at 2 times 3 is 6 equals to 4. So that's why this formula does make sense. And that is the end of example 18. And let's move on, okay? Next, now we're going to do a whole bunch of stuff. Let's look at example 19 on the following page. I guess I'll erase the board. I should mention that actually to write it this way, I should mention this is more of a compression with a number b if b is bigger than 1. And the bigger the b is you're actually squeezing it together like how our previous example that we just mentioned. They end up being that g for f to be compressed into g like this, right? What actually happened is that then G is actually equal to F times F of 3x. So that is just how it works out, and we'll see more of that in a moment. So anyway, so let's look at example 19, where we are supposed to do, and by the way, please do all the examples I listed under the video description as part of your homework as well, as always, okay? I write down which ones to skip. So the ones that I say skip, please don't bother doing them. You're wasting your time. And so anyway, here's the compression problems. I mean, example 19, let's look at what we're supposed to do here. So in example 19, we have, let me write it down. So example 19, we're on page 278. We have G of x is defined as 2 of f of 3x plus 1, where f of x is given in this chart. F of x's domain is only defined for 4 numbers. And then we're supposed to figure out what G of x is and fill it into this number. Now that's simple enough to do, if especially if you have a calculator. And so I'm going to pull out my calculator and make this thing come out. So what are we doing? F of x, if x is 6, f of x is 10. So f of 3x is, let me think about this. Right. First, we need to redefine the domain because the x only has 4 values that it makes sense. So for g of x to make sense, then we need to, and g of x works on, is f of 3x. So we divide all these things, okay, to come out with the 4 values that'll work in this situation. So divide all these numbers by 3. We have 2, 4, and 6, and then that divide by 3 becomes 12. No, what am I saying? No, it doesn't. It becomes 8. Okay, so that is in the sense that if you enter these values as defined by g of x, then you have 2 in here it becomes 6, then it will be f is defined as 6. Similarly, if you enter g of x as 4, okay, 4 goes in here, is 12 is defined here, and so on. So we are redefining the domain to fit the definition of f. This isn't normally done, but in this case we do it because f of x domain is strictly limited. Okay, it only has four values in the domain. Okay, so now that we've done that, so g of x equals the domain will be 2, 4, 6, 8, and when we plug it in, then so the next step is we achieve f of 3x will become of course will become this stuff. Okay, so it is. And then, but we're going to continue calculating. f of 3x is this stuff, and then we'll multiply by 2 and then plus 1. So then 10 times 2, so the first value is 10 times 2, 20 plus 1, 21. The second value times 2, 28 plus 1 is 29. The third value times 2, 30 plus 1 is 31. And the fourth value, which is this end up being here, times 2, 34, and then becomes 35. And that should be the value of g of x. We don't need f of x here. This is the definite, so this will be the final chart for g of x. The only difficult or unusual thing to do here is because f of x domain is so limited, we have to redesign g of x domain to have everything make sense. And that should be, yep, 21, 29, 31, 35. That is the right answer. Now, so next, let's look at example 20 below the page where we consider, let's see, we have this thing here. So example 20, let's look at this. Example 20, we have, let's see, what are we doing here? All right, let me write down the function. Okay, so let's do problem 20. We have f of x equal to all this stuff. This is what we start with. Okay, and this is f of x. This is the new one, which is not f of x. I should write down this is g of x, and that's what we're looking for. Okay, here's the new function, g of x, which is g of x is built up with f and some other stuff added. So first, we to transform f of x into g of x, first we do the, let's see what happens with the 1/2 trick. So f of 1/2 x, let's draw here, okay? F of 1/2 x then is, I want to do f of just 1/2 x. Your book does it slightly differently, and I don't think it matters either way how we do it, but I'm going to try and see what happens, okay? So I'll only do this part first. So transforming this thing to 1/2 x, that means when x is, see, in this case, when x is 2, f of x is 0, okay? So for that to happen, then x has to be 4 for f of x, so then it becomes 2, and then it becomes 0. So this graph is stretched. See, as I have mentioned before, that the horizontal compression is when you stick a number b, in this case we have 1/2, because if b is bigger than 0, then it becomes a compression. But if in this case b is 1/2, so we're actually stretching it. So then your circle-like, half circle-like thing is now being stretched both ways like that. Okay, so that is so far so good. So the next step we're going to do is do the +1 thing, which is right here. Okay, we have learned a bit earlier that x minus a, when a is positive moves to the right, negative moves to the left. Now, because this is a plus sign, that's the plus is the same as minus, so a is negative. Okay, so we're going to move this thing to the left one step. So the next graph we're going to draw, okay, we'll go over here. So the next graph is everything got moved over one step. So the semicircle will go from 3 to -5 because I'm moving everything over one step to the left, okay? Because a is negative now. And so we'll draw it like this, something like that. But otherwise the graph still looks the same. Okay, so that is, so this part, I have now got to f of 1/2 x plus 1. X, where's my x? Plus 1, okay? And then, so the next step, and let me check to make sure I got it right. Actually, I think I'm missing some details. It's better to let's just stick with what the book says, is do this instead and not worry about anything. So first, before we do this stretching, we're going to rewrite this equation. Okay, just like your book says, we will rewrite this thing by factoring. So before we worry about the translation or squeezing or anything, we'll rewrite this formula like this. We'll rewrite this thing as f of 1/2 of x plus 2. And the reason is because 1/2 of x plus 2 is the same as 1/2 x plus 1. So that the rest stays the same, okay? And then having done that, we'll do this one. And the next thing, what we're gonna do is, once we've done the 1/2, the next thing we're gonna do the plus 2, which now becomes minus -2. So that is the a that we referred earlier. So we'll move the graph 2 steps to the left. And therefore, this graph now looks something like this. So it's 2, goes up, down, okay? So it goes from 2 and then to -6. And finally, we're going to actually push down the graph by 3 units. And so the final graph then will look, imagine this thing go down 3 units, and that is the result of, where's the pushing down 3 units? Is it the next page? Yep, here it is. So the final graph is on the next page, where you see the thing got pushed down by 3 units, and that is the solution. This step is crucial though, because I forgot that if you do it this way, you're not actually exactly following the definition of this thing. So this step is, so don't forget to do this step. That is this particular factoring, so that the fraction includes the whole thing, okay, for everything to work out. So for homework, I have a bunch of homework here, so I won't read them out, but they are mostly very short. This one is a little bit longer, but most of them, they're very short. So if you just go by the set of rules here, I have written here, and there's probably some other rules, and the book probably have something like that as well. So please get your homework done, and then when you finished, I want to talk about some of them. So problem 29, now that you're done with your homework, let's look at it. K of x equal to x minus 2 to the 3rd power minus 1. The fact that there's a k here is instead of an f makes no difference whatsoever. Okay, so we start with the function y equal to x cubed, because that's basically what's happening here. And if you look at the toolkit's function a bit earlier, y equal to x cubed looks something like this. It crosses down to the level and then cross down again, something like that. Now, although I should have drawn this part a little bit more level, okay, it kind of levels here. But anyway, whatever it looks something like this, okay? And we need to push it to the right as when a is positive, we're subtracting by a. A is positive means we push it to the right 2 units, and then we push it down 1 unit. So here's the new graph. So we push it to the right and then down. So something like this, okay? That should be a good enough answer, and the answer in the back book looks kind of like that too. So that's that. Next, let's look at problem 37, where we are just given the graph and try to figure out what the equation might be. Now, by looking at this thing, this looks like y equal to x squared, right? So we'll start out with y equal to x squared, except that now the bottom, instead of, normally y equal to x squared look like this, with the bottom of the parabola hitting at the origin. But now the bottom is pushed over at positive 2. So we'll follow this rule, okay? A is positive, so it will be the function of, instead of x squared, it will be x minus 2 squared, because it seems to have been pushed over to 2 units. See, the bottom hits at 2. So let's look at the answer, and that, I think, what are we doing here? This is 37. Okay, 37, yep. F of x equal to x minus 2 squared. That is the correct answer. So next, let's talk about problem 61, where we have a function that has 2 things done to it. First, we have, so g of x equal to, I'll just write it down here, g of x equal to 3 times f of negative x. Now, we don't know what the function f look like, okay? So we can still imagine it by drawing anything. Let's say the function looks like this, like a semicircle. I'm just making this up to give you an idea. So first, we're going to slap the negative x in there, which means that we're going to flip it which way? We're going to flip it right here. See? So slap the negative x, we're going to flip it against the y-axis. So then it looks like this. So the first step, this function will be flipped against the y-axis, so now it looks something like this, okay? And secondly, we're going to multiply by 3 times, so that when you have a multiplication like this, see, a number being multiplied with the function, that is a vertical stretch. So we're going to stretch this thing 3 times, but maintain the same width, okay? So now it's going to look like something like this, 3 times, so something like this. So if the function were as a semicircle, I just use that as an example to give you an impression. So the answer is that the function is flipped across the y-axis, and then it got vertically stretched by a factor of 3, as the answer says. All right, so next let's, oh, by the way, the previous problem was 61. I don't know if I even said that. So next problem we'll talk about is problem 65, where the graph is vertically compressed by a factor of 1/3. Okay, so 65 we have already here. So 65, well, our original function is f of x equal to, what is that? 1 over x squared. All right. And then we are going to first vertically compress it by 1/3. So we'll write down 1/3 on it. So now we have 1/3 x squared. And then next we are going to shift it to the left 2 units. Now to shift it to the left, that's the same as minus the negative of the 2 units. So in other words, plus 2. So the next step we will have 1 over 3x plus 2. Okay, because we're shifting to the left. So, or put it another way, it's minus negative 2. And then finally, we are going to shift it down 3 units. Down 3 units, just simply minus 3, and that should be our answer. That looks correct. That is what the book has. So we'll take that as the right answer. And let's move on to the next problem. So the next problem, we'll do problem 75, where we have p of x is 1/3 x to the power 3. So that's the same as this. Here's the y equal to x to the power 3 function. But we're going to stick 1/3 in there, which means that we're going to do a horizontal compression. Well, in this case, stretch. Okay, when the number is big, it's a compression. When its number is small, it's the opposite of compression. So we're going to stretch it horizontally by 3 times, basically, is what it means. So that thing is going to look a lot flatter. So that's the first step is we'll stretch this thing horizontally. So now it looks stretch like that, okay? And then next, we're going to push it down by 3 units, because that's what the minus 3 is. Minus 3 just means, well, see, when b is minus, we'll push it down. It's that simple. And so let's move that down 3 units, and that will be it. So to draw that, I guess we will have, here's the line, and now this thing is something like that, okay? Imagine it's down by 3 units. And that should be the right answer. So what problem is this, 75? Yep, that looks about right. And that marks the end of this section.